Welcome back, students, to a new chapter, that is ferroelectric properties of matter. In this, the module name is structural phase transition and classification of these ferroelectric crystals. I am Manjunath Nayak from Carmel's College, Noe. Here, we will learn about the structural phase transition in ferroelectric material, classification of these ferroelectric crystals. At the end of the module, you will know what is a ferroelectric material, and you will also know about different ferroelectric material and the phase transitions that occur in this material. So to begin with, let me just explain you what is ferroelectric material. Okay, now don't get carried away by the word ferro in this particular term, ferroelectric. Just the way it was told to you in ferromagnetism, that it is named because most of the time, or the first material that was found to be magnetic had iron in it, and the word ferro was derived from it. Okay, whereas ferroelectric material has nothing to do with iron. The word ferroelectric is taken as an analogy to ferromagnetism. Okay, just in ferromagnetism you had spontaneous magnetization, even whether the magnetic field was applied or not applied, there was a spontaneous magnetization, or there was already a magnetic field in this particular material in ferro, and those materials were called ferromagnet. Similarly, here we have ferroelectric materials, which are actually a dielectric material, and they have spontaneous electric dipole moment. Please note, they have spontaneous electric dipole moment even in the absence of external electric field. Okay, so even if you have not applied an external electric field, there is a spontaneous electric dipole moment in this material. Okay, and this happens at sufficiently low temperature, and we will discuss different materials, and you will know that there are some material in which it occurs even at little bit higher temperatures also. So they are called ferroelectrics, as I told you, in analogy with ferromagnetics, which have spontaneous magnetic dipoles, okay, without external magnetic field. Now the phenomena of existence of spontaneous polarization, that is electric dipole, in dielectric material in the absence of electric field is called ferroelectric effect. Okay. Now the existence of spontaneous polarization is necessary. Okay, so if for a ferroelectric material the spontaneous polarization is a must, but that is not the only sufficient condition. You cannot call any material ferroelectric just because it has a spontaneous dipole moments or in this material. Okay, the ferroelectric should even lack inversion. Okay, it should not have an inversion center in them. That is the center of positive charge, and the crystal should not coincide with the center of negative charge. For example, I've just drawn a simple diagram here. You can see charge, let's say negative charge AB. You can see distance AO and distance BO are exactly equal. So obviously they will have the center of inversion in them. So this particular combination cannot be ferroelectric. Similarly, I have a say positive charge. DO and OC are same. So I cannot call these a ferroelectric. They will not show ferroelectricity just because they have the inversion center. Okay, so they should lack the inversion center. That's a very important condition for a ferroelectric material. Now, besides the center of inversion, there are other elements of symmetry such as the planes of symmetry and axes of symmetry. A combination of such symmetry elements can also eliminate the possibility of any existence of this ferroelectricity. Fine. So that is the reason among 32 crystal classes that we have, 12 classes have center of inversions, and therefore they can just never be ferroelectric anytime. Notably among them are copper sulfates, which are triclinic, calcium sulfate with 2 molecules of water, monoclinic, barium sulfate is orthorhombic, and so on. Okay, so we cannot just having the dipole moment is not enough. It should not even have the center of inversions. Okay, the symmetry should not be existing, any form of symmetry. So the classification of ferroelectrics and structural phase transitions. So mostly known ferroelectric materials are classified into 3 main groups. Okay, the first one is a Rochelle salt, second is a potassium dihydrogen phosphate, and third is a barium titanate. We will go in detail about each one of them. The Rochelle salt is numbered as 1, as that was the first one that was found or studied, and then the later one also are studied. So beginning with the first one, that is a Rochelle salt. It's a crystal, the first crystal to be discovered or known as a ferroelectric crystal. Okay, and the composition, the chemical composition of it is sodium, potassium, 4 molecules of carbon, 4 molecules of hydrogen, 6 molecules of oxygen, all together with 4 molecules of water. The simple chemical name for this is double tartarate of sodium and potassium with 4 molecules of water. Okay, this is the chemical name of this. Now, if I look into the feature of this, then let the temperature increase towards your right. Then it is in an orthorhombic phase at a temperature higher than or up to 296 Kelvin. Okay, so just take your calculator, punch in and check what is 296 Kelvin, subtract it with 273. Okay, so up to that temperature it is orthorhombic, and below that there is a monoclinic phase. Okay, so below that is a monoclinic phase, and this monoclinic phase exists only up to 255 Kelvin, not much. It exists only up to 255 Kelvin. So you have just a region of 20 degrees Celsius before it undergoes another phase transition, that is rhombic. Okay, so orthorhombic and rhombic are non-ferroelectric phase of Rochelle salt. Listen carefully, it is a non-ferroelectric phase of Rochelle salt. So Rochelle salt shows ferroelectricity only in the monoclinic phase, that is between 255 and 296 Kelvin. This particular temperature has a special term called Curie temperature. Okay, beyond this and before this, the phase changes as a phase transition. It's called Curie temperature. Okay, and Rochelle salt is one of those very few material which has two phase transition temperature, and one at 296 and one at 255. And in between that, where there is a monoclinic phase, recollect from your chapter 1 what is monoclinic phase. Okay, in this monoclinic phase, it shows ferroelectricity. So as you can see in this diagram, right in just below monoclinic, there is an hysteresis that is drawn. Detail about this hysteresis, the PE curve, you will learn in the next module. But as you can see, there is a hysteresis that is formed. So you can see there is a spontaneous polarization that is happening only in that monoclinic phase. Before that, that is in orthorhombic and rhombic, it is not a ferroelectric material. Fine. So the formula for Rochelle salt, as I told you, is in blue color. Now it is found that if you change the water to a heavy water means deuterium, if you simply change the water H to deuterium D, then surprisingly it is found, this blue one is for the one with water, 4 molecules of water. It is found that the range of temperature in which it remains ferroelectric material increases. Okay, simply increases by simply replacing hydrogen with heavy water, even though there is no much difference in terms of its molecular weight and all other characteristics. Of course, deuterium is the isotope, but even though there is no much change in the other characters of it, still it is found that the range in which it shows ferroelectricity increases by almost 20 kelvins. And this extraordinary isotope shift is believed to be the quantum effect involving the mass dependence of the de Broglie wavelength. Deuterium substitution also changes the spontaneous polarization and the coercive force. Moving to the next interesting ferroelectric material, that is potassium dihydrogen phosphate. It is most important member of the tetragonal phosphate group of a ferroelectric materials, KH2PO4, that is potassium dihydrogen phosphate. In contrast to the Rochelle salt, it has only one Curie temperature. In case of Rochelle salt, you had two Curie temperatures where the phase transition would take place. Here it has only one Curie temperature, that is 123 Kelvin. Above this Curie temperature, the crystal has a tetragonal structure, and below the Curie temperature, it has an orthorhombic structure. And this is because of the C-axis, that is the direction along which the spontaneous polarization that will occur. From an analysis of the structure of KH2PO4, that is potassium dihydrogen phosphate, it appears that the PO4 group forms a tetrahedron with 4 oxygen at the corners and the phosphorus at the center. These phosphate groups are bound together by what is known as hydrogen bond, and in these bonds the proton may occupy a number of possible positions, each of which corresponds to a certain polarization of the unit cell. Here also, replacing the hydrogen by deuterium raises the Curie temperature from drastic 123 Kelvin to 213 Kelvins. Okay, almost an increase of 90 Kelvin. and it thus is fairly certain that the hydrogen bonds are essential in polarization of a group of ferroelectrics. Moving on to the most studied or most researched ferroelectric, that is barium titanate, which was found by Weiner and Salomon in 1942, and they observed a number of anomalous dielectric properties of this barium titanate. It has been most thoroughly investigated and best understood till date material among the ferroelectrics. This is the third group, as I told you, and that is this is an oxygen octahedron group. This group can be subdivided into others, one of which is the subgroup of perovskites. Okay, perovskite is a very hot topic in research also, with general chemical formula of AbO3, where A is taken by a di or a monovalent metal. Okay, in this case it's barium. B is a tetra or a pentavalent metal. In this case it's titanium, and O for O3. So BaTiO3 is the most important and the most thoroughly studied representative of the perovskites because of its property of being ferroelectric material. Now, in the non-polarized phase, it has cubic symmetry. The Ba2 plus ion occupy the corners of the cube. The oxygen ions are located at the centers of the faces, and the TiO4 plus ions are at the center. Typically, for barium titanate structure and for other members of the group is the arrangement of the highly polarizable oxygen ions in the form of octahedron, which a small metallic ion at the center. So, barium titanate has an upper transition temperature of 120 degrees Celsius, that is 393 Kelvin, and that is the reason it is researched so much. It becomes so important because its transition temperature is 120 degrees Celsius, higher than anybody, and above this temperature it is non-ferroelectric. Okay, now it has three structural phases. Surprisingly, it has three structural phases. One is a cubic, tetragonal, orthorhombic, and rhombohedral. And out of these four, only cubic is the one which is non-ferroelectric. Rest all, that is tetrahedral, orthorhombic, rhombohedral, all these three are ferroelectric, whereas only cubic is a non-ferroelectric among all these four. Okay, so let's simply see in summary the table about how this happens. So cubic, as I told you, is a non-ferroelectric, so that is of no interest to us. But tetragonal appears in the temperature region of 278 to 393 Kelvin, which is very good for us because this is the temperature we can deal with very easily without any cryo cooling. Next is orthorhombic, which appears at around 193 Kelvin to 278 Kelvin. And below 193 Kelvin also it is rhombohedral, which is also a ferroelectric material. So here is a summary of all this, and remember only the cubic one is a non-ferroelectric material, and that's why we ignore it. You can read more about this in the references that are listed below here. I hope you enjoyed this module. Thank you.